Okay, yeah. Okay, now let's look at how we can solve this equation, right? How we can solve this equation. And then we will see, then there is no, we will see, actually, the model pulse propagation. So model pulse propagation, right? Model pulse propagation. First, in the physics convention, we may write Fourier transform form in the way that this is UZT as the 1/2 pi infinite, negative infinity to infinity d omega u omega hat and u z omega exponential negative I omega t, right? So I use the u hat as the function in the Fourier domain, right? I use the u hat as a function in Fourier domain. So UZT is 1/2 pi d omega u hat z omega exponential negative I omega t. And u hat, this is the inverse Fourier transform, right? So inverse Fourier transform, and u d omega hat is negative infinity infinity dt u zt exponential I omega t, right? So this is the Fourier transform pair. U is the function in time domain. And u hat is the function in the frequency domain, right? I use the z. Z is the you can consider as a propagation direction, right? And some of Fourier transform, they split the 1/2 pi to 1/2 pi. One of the square root of 2 pi here, another one of square root of 2 pi there. But this is what we use mostly, in the physics convention, right? Okay, so now we'll look at the second case, right? So we have the Fourier transform is the basics of the wave linear, is the fundamental. The Fourier transform, Fourier transform is fundamental to linear wave propagation, right? Let's see. Fourier transform is fundamental to linear wave propagation. So this, let me use an acronym FT. Fourier transform, right? Fourier transform is fundamental to linear wave propagation, right? In time domain, let's have this equation as I partial u zt over partial z plus ik not prime partial u zt over partial t, right? And I'm just copying the equation, and then minus 1/2 k naught double prime partial u zt partial t second order, right? And minus I over 6 K naught triple prime partial U partial T cube ZT equals 0 plus all the high order term, right? High order term. Okay. Okay. Now let's take a Fourier transform, right? Let's take a Fourier transform, which we will get is in the Fourier transform in the Fourier domain. Right? In the Fourier domain, let me find out in the Fourier domain that is it is the I omega, right? So that's the df, yeah. Okay. In the Fourier domain, let's take let's take a Fourier domain here. It is I partial U hat Z omega dz, right? Partial U hat dz. And then because if I take a Fourier transform of this U zt, what I got is U z omega, right? Just simply get the I omega. And then one thing we recall, right? If you look up from our previous a Fourier transform of this partial U zt partial t, if you look up your previous notes, it is equal to, right? So this the Fourier transform is negative I omega, right? So U z omega. So if you take a Fourier transform, this is I think we did the first class, right? If you look at check your notes. We did the first class. If I take a U on the derivative, what we have is negative I omega. It's not negative I omega. So this will be negative omega plus I k naught prime negative I omega, right? And U z omega. And that's the hat. Then let's have the minus 1 over 2 k naught double prime. Now we have second derivative. What happened on the second derivative? It is square, right? So this is minus I omega square U z omega, right? So that's this case. Because it's second derivative, I omega square. Then let's have minus I over 6 k naught triple prime negative I omega cube U z omega, and all the higher order term equal to 0. Okay. Okay. Let me write it. Let me read it. Right. So it's I partial U partial Z of U hat Z omega plus I k naught prime left parenthesis negative I omega U hat Z omega minus half k naught double prime left parenthesis negative I omega right parenthesis square U Z omega minus I over 6 k naught triple prime negative I omega square, right? Cube. So now what we have is I partial U partial Z and the Z omega, right? I just copy plus I plus this I. Oh, so this I and negative I cancel out. So it's positive, right? So it's K naught prime. U Z omega, I'm going to use it later on. So negative I square is just simply negative. Negative I square is just simply negative. So plus K naught double prime over 2, right? So negative I cube. So let's say negative I times negative I times negative I. Altogether, negative cancel out. I is negative. So this is just simply positive I, right? So negative I cube is just simply positive I is negative 1. So it's plus K naught triple prime over 6 plus all the higher order term. Then we have U Z omega equals 0.
What happened to all of the omegas?
Oh, thank you. Thanks for pointing it out. I just missed the omega. It is actually K naught omega there.
Okay.
Thank you. Plus omega cube. Yeah, thanks for pointing it out. Yeah. You you guys can always, find out my typo. So that's good. Okay, great. So that's the actual omega there, right? So if you look it up, if you look up this equation, this sounds familiar. What is this term? I mean, all this term in the box. You can check out by your previous notes. What is this term?
Is it a Taylor series?
That's very good. It is Taylor series, right? That's very good. It is the Taylor series for the K omega minus omega naught. So it is the Taylor's expansion series minus this constant term, right? If I have a Taylor series and then I have K naught and K naught prime, omega plus K naught prime, double prime over 2, omega square plus K naught double prime over 3 factorial, right? Over this term. So it's nicely met together, and this is the Taylor series. So the equation is, in Fourier transform, what we have is I partial U hat Z omega over with respect to Z plus K omega Taylor expansion at the zero frequency, right? But this is the carrier frequency actually. This is the shifted. Remember, it is the shifted K, right? Shifted K minus K naught. And then we have U Z omega hat equal to 0, right? So this actually writing include all the high order term, right? So we just derive this pulse propagation equation. And you will notice that if I miss the omega, it won't work, right? If I miss the omega, it won't work. Thanks for reminding us. Good. Now next we will solve this equation, right? So we will solve this equation, and in this case we get we will take a partial derivative and we move this u hat on the left hand side, dz, right, partial z to the right hand side, right? So it's the partial u z omega hat. It is a hat divided by u hat, and z omega on the right hand side become negative. Since I moved the I, so so it become positive. So it's I k omega minus k naught, and then partial z, right? Partial z. So now this is much a better way of writing this, right? This equation. Okay, questions? Okay, so now we are a better shape, right? Then we take integral. Let's take integral. So it's the partial u over u. Anyone can remind us what kind of the function would be for the integral?
Would it be a natural log?
Natural log, thank you. Yeah, it is the natural log, right? It is natural log of u hat z omega, thank you. And then we integrate from 0 to z, right? We weigh propagation from 0 to z. On the right-hand side, we have I k omega minus k naught, and z from 0 to z also. So we're propagating from the z, right? It's the integral of the dz, so it's the 0 to z. So on the left-hand side, it's the natural log of u z omega over u 0 omega, right? On the right-hand side, just simply I k omega minus k naught z, right? And then we can simply solve this equation. So that is the u z omega, and this is the natural log, and we put the exponential there. So it's u 0 omega, and shift to the right hand side, take the exponential I k omega minus k naught and z. Now this equation is complete, right? It doesn't include it does not include Taylor expansion. It's not rely. It is not rely on the Taylor's expansion, but rather it's a complete process. Right? And I forgot the u hat. And before you remind me, this time I remind myself. Right? Okay, so this is a u hat. This is u hat. Okay. Okay, so now what does it mean? It means that in the frequency domain, the signal at z equal to 0 and the signal at z equal to z has this relationship, right? So now let's look at a chart. Right? So that is this piece, right? So I'm going to look at u 0 omega, 0t, sorry. This is 0t. This is the 0t. And then the first one, let's do the Fourier transform. We will get u 0 omega, right? So we first get the Fourier transform at the original point. We take a Fourier transform, and then at the after that we propagate, right? We propagate, become u z omega, right? Using what? This equation, right? Using this equation. So let's say this is the equation 1, right? So this is the equation 1. So use this equation to propagate my signal. So now it is propagate the frequency domain at the beginning of the fiber. This is the frequency domain at the end of the fiber. Then what happened? UZT and take a inverse Fourier transform. Inverse Fourier transform. And it at the end we reach the ZT, which is the time domain at the end of the fiber, right? So although what we want is UZT to U0T to UZT, but the direct path is actually difficult, right? We have the pulse, we have different pulse, we have this pulse, and we want to propagate. And each time the frequency component have different delay, right? Different, it propagate at different speed. It's really hard to propagate directly. Instead, we take a Fourier transform. And then we propagate the signal in frequency domain, and then we come back, right? Then we come back. Okay, now you may ask, it's really complicated, right? I need to do a Fourier transform and then propagate. Then I need to do an inverse Fourier transform. You think it's actually quite complicated. However, in the MATLAB, for both Fourier transform and inverse Fourier transform, it's already been written. It's a standard package. So it is standard package. We don't need to do all this Fourier transform and inverse Fourier transform. It is a rather standard process. So what we need to worry about, need to consider is just writing this. Just include this process into this picture, the schematic, then taking a Fourier transform and inverse Fourier transform. That's the pulse propagation. And any questions?
Dr. Go?
Yes.
So this MATLAB lab that you're talking about, is this what we're going to be doing in the lab?
Yes. That's what we're going to do. We're going to actually write the code. Or actually, you don't need to write the code, but I'm going to give you, so this code already been written. This is the code already being written. As long as you can use it and understand it. So we're going to have the lab session and we will do it together to understand the mechanism. Basically, what my goal is to provide the code so you can see what happened in this process. Yeah. And also, if you feel complicated, we'll work together. It's not that you need to write the whole thing, but instead, I will provide the basic code as long as you can change some of the parameter, as long as you understand the mechanism, that's fine. Yeah. I know the whole thing is more like a research style topic. It's actually my research. So this style, getting whole thing done require a lot of effort, but we'll just touch the basics. I will provide some of the basic code. You will revise it. So this is our lab session. So you require to have the MATLAB in your computer. If you have problem getting, I think everybody can get a MATLAB from Baylor. But if you have problem getting a MATLAB, let me know. Alternatively, you can go to ECS. You can go to Rogers. Any computer has MATLAB there, but you need to share your screen. Just like I shared my screen, you need to, if you want to ask question, you need to share your screen. So and you need to be able to talk. So find a quiet place in Rogers, and you should be able to to talk right during the class. So this is the lab session I'm referring to. Yes. So if you have problem running a MATLAB in your laptop or getting a MATLAB machine, let me know. By this Wednesday, so I'll see if we can have some solution. Yeah, and all the Baylor students should be able to install MATLAB in your laptop. Yeah. More questions? Okay, so let's look at the main steps, right? I think that's the main step. But let me just so write it down, right? Solve the wave propagation. We first determine U hat. This is hat. I keep forgetting. This is U, this is hat, right? U hat. 0 omega from U0t. Use Fourier transform by using Fourier transform, right? Fourier transform. So we first use Fourier transform to determine U0 omega from ZT, right? We then determine Z omega, right? Using equation 1, right? This equation. Then we use finally we determine UZT from U hat Z omega by using inverse Fourier transform, right? Finally, so there's a step 1, step A, step B, step C, right? Finally, we determine, let me read. We solve the wave propagation. We first, to solve the wave propagation, we first determine U hat 0 omega from U0t by using Fourier transform. We then determine U hat Z omega using equation 1. Finally, we determine UZT from Z hat U hat Z omega by using inverse Fourier transform. And those Fourier transform and inverse Fourier transform already been provided by MATLAB. Okay. Okay. So this is the dispersion effect. I'm going to cover nonlinear effect later on, but this is dispersion effect. Yeah. Okay. Questions? Okay. So now in order to do it, most of this analysis is continuous wave, right? As ZT. But in order to analyze the result by MATLAB, we need to discretize it. So we cannot, we need to do digital Fourier transform, right? Digitized Fourier transform. Yeah. Digitized and discretized it, right? To express, so to express the Fourier transform, we must discretize it. We must discretize it. Because in our MATLAB, everything is discretized, right? We have a pulse, it's not a continuous pulse, it's the discretized pulse. So the usual discretized Fourier transform, right? It's written the usual discretized Fourier transform is written as, so the usual discretized Fourier transform, so this DFT, right? Discretized Fourier transform is written as the, let me use on the top also, as the DFT. So it is corresponding to Fourier transform, right? But now it's discretized. So it's DFT as AN hat as integral m from 0 to capital N minus 1. So AM exponential 2 pi I m n over capital N. And then it's the inverse discretized Fourier transform is AM is 1 over N. So it's corresponding to the inverse Fourier transform, right? So, and N from 0 to N minus 1, that's the total number. AN, right, hat, AN hat, exponential, negative 2 pi I, MN over capital N, MN over capital N. So this is the Fourier transform, but now it's the discretized, right? Discretized. So it's AM exponential 2 pi I MN over N. And here is AM 1 over N, N minus 1. This is N, right? AN, this is hat, corresponding to the frequency domain. Exponential negative 2 pi I MN over capital N. So this is a discretized. I'm going to talk more about it later also, but we'll just gradually going through, right? So stay with me. Let me see. Let us see what is T, right? T is M times delta T. So M is the index. M is index. Delta T is the steps in time window. So what is a T? T is M times delta T. Okay, so what is delta T? Is T is the total T divided by N, right? It's the total T divided by N. Now we have what is omega? Omega is N, right? So in frequency domain, it's n times delta omega. Delta omega, right? Okay. What is delta omega? Delta omega is 2 pi f, right? 2 pi delta f. So it's 2 pi. What is delta f? F is 1 over t. Right? 1 over t. So this is the delta f. Okay. So it has this relationship, right? Delta f is the 2 pi over delta 2 pi over capital T. Capital T is in the time window. This is the omega. Okay, so that actually is the same as Fourier transform, right? So we note that m equal to 0. That's the first point, right? M equal to 0. It's the 0. M corresponds to t equal to 0, right? Corresponds to t equal to 0, right? M equal to 0 corresponds to t equal to 0. And n equal to 0, corresponds to omega equal to 0. So t, when we actually write it, we need to be careful on what it is corresponding to, right? And then we let it go the time domain. In time domain, right? And t is from negative t over 2 to positive t over 2, right? If I have a pulse, right? If I have a pulse here, and then I will have this, and this in the center is m equal to 0, right? If it is Gaussian pulse, and then we discretize it, I'm actually exaggerate a little bit, but usually delta t is way smaller than what I draw here, right? But I just want to make it clear for you to see, right? It's a Gaussian pulse. So this will be m equal to 0. In here, it's m equal to 1, m equal to 2, m equal to 3, right? So this is m equal to 0, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Because when m is 0, it corresponds to t equal to 0, right? Then we need to actually shift it, right? Then we need to shift it. So let's say so t values can be negative. T value can be negative, while m value cannot, right? While m values are not, right? Because in the t value, it's a positive t value, but m value cannot be negative. That's then n is the total number of points, right? N is the total number of points. And also delta t is total t over n, right? So this is the delta t. This is the delta t. So delta t, let me write it. It's the delta t, right? This is the delta t. Delta t is the total t time in span divided by capital N. Okay. We also know that M values are circular. We also note that M values are circular. Because we learned from the signal systems class, right? When we take a Fourier transform discretized, it's actually, we have time window, it's a periodic signal. It is a periodic signal. It is periodic in time domain, and also it is periodic in frequency domain, right? That's what we learned from the signal systems class. It is M values are periodic. The M equal to N, let me write. M equal to capital N is the same as M equal to 0, right? M equal to 0. Yeah. So now we can write, we can discretize it, right? Now we can discretize it. Now, so this is the in the time domain. Now we can discretize it. The time domain, right? We can discretize the time domain. Sorry for bad handwriting, but instead we start from 0, right? We start M from 0, 1, 2, M 1, 2, right? M is 1, M is 0, M is 1, M is 2, right? So we got this pulse going down, and then going further down, right? So it's 1. So this is M equal to 0, 1, 2, 3, right? 1, 2, 3, and then we will do. We have a lot of points, right? We have a lot of points at here. This is M equal to N. This is N minus 1. This is N minus 2. And then I have the point here because M equal to N, capital N, that's the total points. If M equal to capital N, that's the same point. And then M equal to negative N minus 1 here, right here, right? But keep in mind, so this is a pulse, right? It's a Gaussian pulse, for example, it's going up, right? But this I'm drawing actually this piece, that piece 0, 1, 2, 3 is this piece right here on the right shoulder, and this is negative 1, right? On the left shoulder, it is actually moving towards the right. The reason is that it is actually a periodic signal, right? It is a periodic signal. So originally, this should be here. This should be here, right? But we don't do the negative in the M, right? In time domain, there's negative, but in discretized Fourier transform, there is no negative here. But we, instead of half t to half t to negative half t to positive half t, we will just look at the window at 0 to t, 0 to t. But they are the same, right? But they're the same because it's periodic. It is there is a going down, going up, going down. It's a periodic signal. What we take is the region from 0 to n, 0 to n. But keep in mind, this centerpiece is the highest value is at m equal to 0, right? Those two, they are the same. Those two, they are the same. Okay, so let me finish with those two, with these two things, right? Then we're done for today. Okay, let me finish. The mistakes that you can make, right? Mistakes that you can make. First is forgetting to shift the function when discretizing, right? We need to shift, right? Forgetting to shift the function when discretizing. Forgetting to shift the function when discretizing. Second one is when you shift, it is pay attention, shifting the function so that it is symmetric between m and n, right? So you need to, this is, you forget to shift, right? And then you need to shift the function so that it is symmetric between 0 and m minus 1, right? So shifting the function so that it is symmetric between m equal to 0 and m equal to n minus 1, right? So when you shift, pay attention that the maximum number is at m equal to 0, right? So the point m equal to 0, let me write here. I don't have a space. The point m equal to 0 corresponds to t equal to 0, right? Not t equal to half delta t, right? So at here, the maximum number is right here. So it is not in the half delta t, it is in the 0. So the point m equal to n minus 1. So if m equal to n, that's the same as m equal to 0, corresponds to t equal to negative delta t, not t equal to negative delta t over 2. All right. So it is the 0 is the maximum, and at the n minus 1, it is negative delta t. It's this point, right? It is not the half point, right? Instead, for example, let me give you, when I discretize it, I'm not discretizing like this, right? Center and half delta t. So this discretization is wrong. This discretization is wrong, right? The way we discretize is that we need to discretize the center peak as the maximum, right? And then you can see the right shoulder, the red piece is this piece, right? And the left shoulder, which does not include the maximum number, is this piece, right? So is this piece. Okay, questions? Okay, yeah, that's good. So So we're going to have some explanation on the discretized Fourier transform. After that, we'll have an example on how we can analyze the pulse propagation. I'll give you a code, but you should play around with it. Try to at least understand the mechanism. You don't need to write the whole MATLAB code. Instead, you need to use the MATLAB code to understand the physics, in the wave propagation. Okay, so today's the Monday. I will see you on Wednesday. I'll see you on Wednesday. Okay, bye.
Thank you.
Bye.
Thanks, Dr. Hu.
Thank you.